cancel.
Oh yeah, yeah. Do a bad thing to a bad person, and that's good. No, I don't agree. Two wrongs make a right. Are you saying?
In
No.
this sense.
Okay, I know. I'm just joking with you, but I don't agree with two wrongs make a right, but two rights make an airplane. Right? You agree with that? Orville and Wilbur.
No, I rather.
Yeah, two rights make an airplane. uh, so, yeah, that's what you've been told, right? The negatives cancel. But why do they cancel, right? And so you should be kind of pissed off right now if you don't know why a negative times a negative is a positive. You're like, hey, someone just told me that was true, and I had to accept it as blindly accept it. This is not acceptable anymore for us as mathematicians. We want proofs of things, right? And so, but anyway, the negative means opposite, right? So this is when I read this, it's opposite. Multiply means of. -2, opposite of -2 is of course +2, and this negative or opposite piece really only exists in numbers. There's no other negatives. Opposites, I mean, like opposite of left.
Right.
Yeah. Right, or sure. Opposite of right is wrong or left, so we don't know which one, right? Opposite of up. I'm thinking of the Pixar movie, right? So we're in trouble there. Opposite of peanut butter.
Jelly.
No, not jelly. No. So the only thing that really has opposites are numbers. So, but it's that language. I mean, maybe because we learned this in second grade or something that we don't remember why, but we want to know why. So today we're talking about arithmetic sequences, right? We're talking about arithmetic sequences. So 12.2 is all about arithmetic. And what's the key about arithmetic sequences or series? What's the important piece of it?
Like, is the main difference, like the main characteristic is the difference is an integer?
Yeah, well, it doesn't have to be an integer. Could be a decimal fraction, anything, but it's the same every time, right? So, for example, if I start with 2 and then I get to 7 and then 12, you can tell me what's next, right? You're really good at figuring out that the next number is waiting. 17. So you can tell that you're adding 5 every time to get to the next, right? So we call that D, the common difference. Right? Here D is 5 for this particular sequence, right? And the first term, easy to find, is 2, correct? So, and we showed you how to figure out this particular piece using. So since I'm taking that same step every time, this is really related to what's thing that we have studied in the past. Exactly the lines. So when I start, my first term is a height of 2, my second term is a height of 7, right? So I'm always going to take that same kind of step. So we're really relating to lines, and this is why the arithmetic piece is in Calc 1, because in Calc 1 we deal with lines quite a bit, right? In Calc 1, what we do is we take a really complicated curve, right? So something like this, and we'll say, well, let's find the tangent line here. And so I like to think of tangent lines as me skiing, right? I like a snow-covered hill, and I got tunes on, so I'm skiing on the hill, and the slope of my skis at that point is a straight line, or the skis represent a straight line, and I'm trying to figure out the slope of this geese. And we do that all over the curve. So I'm looking at all of these slopes, right? All of these lines. And what's nice about that is now I've taken a curve, right, which is at least x squared, right? Could be x cubed, could be x to the third, and I reduce it back to lines. I reduce it back to an x, right? And that's our whole thing in calculus, is we want to study very complicated things using simple objects. And it's quite beautiful what you can do with just straight lines. And we're good at them, right? And that's one of the things we're trying to do here. Where's my sketch pad? We're trying to, whenever we get to something complicated, if we can reduce it down, right, to something that we already understand, that's helpful for us. But the lines, oh, good, thank you. Yes, Rachel said about sequences of series, practicing helped. Yes, definitely does. But so here, I'll show you how beautiful lines can be. I take a circle. This is a program called Sketchpad, and I create a segment that's one end is touching the circle, the other end is inside the circle. Right? Oops. Sorry. Control Z. And then I'll take the midpoint of this segment, so construct a midpoint, and then a perpendicular through that midpoint, construct perpendicular. This is from conic sections, which I'm hoping to get to at the end of the semester. And then I'm going to trace that perpendicular line. And so now I'm going to move this point around my circle. And as I move that point around the circle, I create, just with the straight lines, I create an ellipse. I create the pattern that the Earth is moving around the sun, right? And and of course the Earth would be a point on that ellipse, and the sun would be, let's say here, right? So we're in summer right now. We're right about here. We're about to move into fall, right? And then we're going to winter when we're on this part of the ellipse. And so just with straight lines, we can create really complicated curves. If I move that point outside, so if I move that point of the segment outside, and erase my traces, and then I move around the circle again, I get the cooling tower. You can see the cooling tower for nuclear power plants, right? Where Homer Simpson works, right? So just from straight lines, we can create curves. And that's one of the aspects of calculus, what we're moving toward, and why these sequences and series are so important to us in pre-calculus, right? So we showed you how to get this with lines, right? So what do? We created an A sub n table, leaving one entry empty. So first term, second term, third term, fourth term. We had 2, 7, 12, 17. Fifth term would be what? 22. And so the 0th term, so since I can add 5, I also am probably pretty good at subtracting 5, right? Sorry, 22. Sorry, I wrote down 5, 22, right? So adding 5, I get to 22. If I keep subtracting 5, I'll get to what? -3 here, right? So I can tell my slope already is y2 minus y1 over, right? Any 2 points, I'm going to get a slope of 5, even if I use 22 and 2, right? So then I get what? 5 minus 1. So that's 20 over 4, and that's still 5, right? So any 2 points, I'm going to get the same slope. And of course, I can get my b value from -3. So we already know that a sub n is 5n minus 3. And so that's the first way I showed you how to get from an arithmetic sequence, how to get the nth term. And then we gave you another formula. And remember, all your formulas you're getting, you're going to put them on a page, front and back, one piece of paper, front and back is fine, of any formulas you want when you take your exams, right? And you're going to keep that. Don't tell my boss. Don't tell other students. I can't stop you from doing it anyway. I'm just trying to make your trying to make it easier for you, right? So we had another version of a sub n of the nth term, right? So our general formula for the nth term is always, I can use an mn plus b, right? Or better yet, our formula that we had last time is the first term plus d times n minus 1, right? And that's the one we're going to use mostly today. So this will generate my nth term. What do I need to use this second formula? I need the first term, and I need the common difference, right? So let's see if that matches up, right? What was my a sub n? Curly brackets, right? I had 2, I had 7, I had 12, right? So I already knew my common difference was 5, and I knew a sub 1 was 2, and I already figured out that a sub n was what? 5n minus 3, is that correct? Is that what I had? Yes? So now using this new box here, right, red black box, what do I get? Well, my first term is 2 plus 5 times n minus 1, right? And it's fine to leave it like that, right? Certainly if Math Excel asks you for the first for the nth term, that's an acceptable answer. Most of us like to simplify it, so I'll distribute the 5, and notice I still get the same thing, 5n minus 3. Why is one of them better than the other? Well, 5n minus 3 is simpler, right? But a sub n, I get to see the first term and the common difference. I guess I can still see the common difference is always my slope, right? You see that? The common difference is always the slope of the line. But I get that first term a little bit better. Of course, if I plug in 1, I get the first term anyway. So, you know, which one is better? Who cares, honestly? You know, I'm always going here. I'm always going here. I'm just going to try and simplify everything as much as I can. And that's from my computer scientist background, is that I want less writing, less code. So we're going to be asked now to find an nth term, to find the first term, to find the common difference, right, etc., and find sums. So that's our big thing today, is finding sums of arithmetic sequences. And it should be kind of obvious that it's difficult to find an infinite sum, right? If I have an infinite term, number of terms, most likely my sum is going to infinity, right? Even if I'm adding up a half every time, right? We're usually going to be looking at finite sums. So let's take a look at that, right? So we're talking about finite sums of finite series. So I might be talking about the sum from k equals 1 to 3 of 5k minus 3, right? The one we just saw, right? And so we're going to be looking at a bunch of ways of finding this sum. One, we could do it just by pure breaking rocks, write out the terms. But if I ask you for 100 terms, a sum of 100 terms is going to be horrible. Then we had our sigma notation that we did last time, right? We're going to look at that again, and then we have a new formula today. So we'll look at all of them. So of course this was what, 2 plus 7 plus 12, is that right? This was my first term, so 21 is what I get, right? I could also turn this, so I can go term by term, right? Not very practical. I can use sigma, and that's what we're going to use in calculus, right? To get this sum using sigma, I'm going to split this sum into 2 pieces, right? So I'm doing 5 times the sum of k, which is an integer, a counter, right? Minus the sum of a constant 3, right? And what did we have for the sum of k? Anybody remember?
K equals 1.
Yeah, n times. Go ahead, Sydney. Cindy, you got it?
K equals 1.
Oh, yeah, in this case, k is going to be 3, right? K is going from 1 to 3,
Oh, okay.
right? But our formula was n times n plus 1 all over 2, right? And then minus 3 times. If I add up 3 n times, I get 3n, right? Where n equals 3. It's always coming from this top number here where I'm stopping. And what do I get there? So I get 5 over 2 times 3 plus 1 minus 3 times 3, right? Everywhere n is, I put in 3, right? Is everybody with me there?
Yes, Rose.
Yeah. And if I'm going too fast, don't let me go too fast, right? Jamal, especially you're right. You're going, what the hell's going on here? And so, but if I'm going too fast, okay, nice. So I get 5 halves times 3 times 4 minus 9, right? 5 halves times 12 minus 9. That's 30 minus 9. Okay, 21 again. So I get the same sum. So we have 2 ways to find the sums of these series. And remember the difference between sequences. Sequences is just my list of numbers, right? In curly brackets, separated by commas, right? And then the series means I'm adding it up. I like to think, it gets serious when you have to add it up. That's, there's that little bit of extra work there. So series, I'm playing with this serious. So we got one more formula today that's new for us, and that is the sum of a sub n, I'll say a sub k, from k equals 1 to n, is the first term plus the last term times an n over 2. So this is our new and of course a sub k must be arithmetic, and n must be finite. I can't do an infinite sum and expect to get an answer. It'll be positive infinity or negative infinity.
Professor?
Yes, Ryan.
I have a question.
Sure.
The sigma, we can also denote it as S subscript n, right?
Yes, and the nth sum. Yes, it's a partial sum. Yeah, that's something you're going to, we don't really talk about, but you'll do it in your Calc 2 class. Look at the sequence, the limit of nth partial sums, and that will be the same as the total sum. And so you may have seen that before, but we'll show that to you. We'll take these concepts that we're doing in Calc 2 in section 8.1 and 8.2 and expand on them and start to include limits with them as well. So I'll prove that to you today, but let's verify that it works for us here, right? So what are we doing? We're taking our same question, see if we get the same sum of 21. We took the sum of k equals 1 to 3 of 5k minus 3, right? So how many terms I have is n. So 1, 2, 3 terms. So 3 over 2. There's my n over 2. I know my first term was 2, and my last term was 12. Everybody okay there? So I'm using this formula now, right? First term was 2, last term was 12, 3 terms, so n is 3. And then I get 3 halves times, what is that, 14? So that's 3 times 7, and again, there it is, 21, same answer. So depending on the situation, I'm going to use one of these 3 ways to find the sum, okay? Or if I force your hand, if I say to you, use the first and last term to find the sum, or use sigma notation to find the sum, right? And so, and Jamal, you're new, but in the first lecture I talked about the 4 formulas that I need for that sigma, right? And they're clearly written in section 12.1 as well, in the textbook. So at this point now, we have everything that we need. We could find an nth term, we could find the common difference, we can find the first term, we can find any term, and we can find sums, right? And that's everything we need for chapter 12, okay? So let's just look at a couple problems, because there's no more teaching to do, it's just practice. And to kind of discover the subtleties of you know, what you need to do. All right, so you'll see me do some things and you're going to go, well, how the hell was I supposed to know to do that? You're not. That's my job, to teach you how to do the problems. And then you just have to practice. So I have an ability to access the whole book at once. Unfortunately, you don't, using MathXL. So I am sorry about that, but I just want to go to the text and do a couple of problems here. What was that, Brian? You okay?
Oh, yes, I am. Sorry, Mom. I just still on.
No problem.
Mom talking.
No problem. Hi, Mom. Oh my God, everything's so slow today. I can't stand it. All right, here's our book. So, yeah, 12.1. I'm ready just to jump right to a couple of problems. So I'm going to just go into our problem, and you know, try the problems in the book. That's a good way to study and to learn. And then you got your homework in MathXL, right? And then of course you could do homework on the in the textbook if you wanted to. So certainly anything up to number 55 is fine. So let's do 55. It says find the sum of the first 120 terms of the sequence, right? But let's do more. Let's find the first term. Let's find the 120th term. Let's find the common difference. Let's find the nth term, and let's find the sum, right? So I'm doing everything there in 55. So 120 terms starting at 14, 16, 18, right? So this is 12.2, number 55. I figure if we could do the last problem, we can do them all, right? So A sub n was 14, 16, 18, right? Dot, dot, dot. Already we know the first term is 14. What's the common difference?
2.
2.
2.
Yep. So our nth term is really quick, right? Our nth term is really quick. A sub n is the first term plus d times n minus 1. Done. Okay. So I certainly can simplify it, right? Which is what? 2n minus 2n plus 12. Is that right?
Yes,
So either one, of course, will generate the 120th term. So A sub 120 just simply means the 120th term. I'm plugging 120 into either formula, right? So 2 times 120 plus 12. That's 240 plus 12. That's 252. Right? We agree there? Nice. And now the sum. So sum from k equals 1 to 120 of a sub k is going to be, well, how many terms is it? It's 120 terms, right? 120 over 2. And I'm going to multiply that by the sum of the first term and the last term. So I get 60, sorry, times what? 166, 266. Is that right? Yeah. And I'm not going to do that one in my head or on paper. Too lazy. 60 times 266. 15,960. Anybody else get there?
Yeah.
Nice.
Yeah.
Not too bad, right? Easy. So, I mean, if that's the last problem, the other ones should be easier. It's not quite true, though. So let's look at a couple of the other homework problems here. But certainly I'm going to ask you to find a sum with sigma. I'm certainly going to ask you to find a sum using the first term and the last term kind of thing. So let's look at another problem. So it, like number 31 gives me the 8th term and the 20th term. So what happens if I've been given the 8th term and the 20th term? So my 8th term is 8 and my 20th term is 44. And don't let me go too fast. If I'm moving on to the next problem too quickly, please let me know. Right? This is 12.2. Number 31, 8th term is 8, 20th term is 44. So a sub 1 is 8, a sub 8 is 8, and a sub 20 is 44. And I want to do the same thing. The book is asking me for less, but I figured if we could do everything, we're good, right? So I want to find first term, in any order I can find these. First term, last term, the common difference, and then the sum. So in this particular sum, I want the 8th term up to the 20th term, right? So, so there's a little subtlety in there that is like, well, where did it come from? And again, I'm not expecting you to know how to do this. You're going to see me do it, and then you'll know how to do it. So I want to take a look at the 8th term here in the form of a sub 1 plus d times n minus 1. But what's the n value? It's 8, right? So 8 minus 1, and that should equal 8, right? So my 8th term, I can put in what I know. And you can see I have two variables there. So the only way to solve two variables, I need two equations. To solve for two unknowns, I need two equations. So I do the same thing with a sub 20. So it's going to be a sub 1 plus the same common difference times 20 minus 1, and that should equal 44. So are you okay with this general idea here, right? Take my general form of the equation, create two equations with it. Now I have two equations, two unknowns. Now I'm back in, 9th grade or whatever grade you took Algebra 1, where you had to solve. You had to find where two lines cross, right? You had to find the intersection point. So we have to find the value of a sub 1 and d. So I'll simplify these first, right? So a sub 20, I got, help me, 19d. And a sub 8, I've got 9d. And now I subtract the two, right? So I take a sub 20 and I subtract a sub 8. And what do I get? The a sub 1s go away, right? The first term goes away. And I get 10d equals, help me,
36, I think.
36, yep. And so I get d equals 36 over 10, or reduce 18 fifths. Now, once I have D, I can, everyone okay? Sarah, you okay there? I saw your light going.
Yeah, I have a question,
Sure,
please.
sure.
So you knew that was the formula because you already like memorized that this is the formula for this problem.
Exactly.
Right? Okay.
Yeah, and I think I had given it Wednesday, right? I think I had given us that a sub n is a sub 1 plus d times n minus 1. And I showed you that it was true, not really a proof, but I took this, right? I took this and I turned it into that mx plus b version, right? We got an mm plus b, right? And so obvious, it's a little bit, I mean, I can do it. I can start from an mn plus b and turn it into this equation, but once you see it one way, you know it goes back the other way. And so, yes, now you're just memorizing it.
Okay.
So, so now I found D, I can now find a sub 1 easily, right? So I know using this formula, a sub 1 plus 18/5 times, what did I do? Did I make a mistake? I did make a mistake. No one caught it. No one caught my mistake. My teachers used to say that I'm making mistakes on purpose. I don't make mistakes on purpose. I made a mistake. What's 8 minus 1? What is 8 minus 1? 7. Thank you. Oh, Robert. So I get 12D equals 36. D is 3. Sorry about that. No one caught my mistake, or you didn't want to correct me. Always, if you see me make a mistake, please fix it. Especially before I move on. All right, so anyway, I can go back into here, right? I can go back into a sub 8 and say that a sub 1 plus 7 times 3 should equal 8, right? So a sub 1 plus 21 should equal 8. So a sub 1 has got to be, help me, negative 13. Thank you.
13.
So we got D, we got a sub 1. We want to be able to write the general form, the nth term, right? And by the way, D can be a fraction, by the way. Don't be afraid of that. So a sub n is negative 13 plus 3D. Sorry, 3 times n minus 1. There's my general form, right? D was 3. And now I'd like the sum. I'd like the sum of I'll use I equals 8 up to 44, right? Remember, because they gave me the 8th term and they gave me the 20th term, sorry, 20th term. Jeez, Robert. Right? Remember, I'm using my subscripts there, or my n values of a sub I, right? So that's the sum of I equals 8 to 20 of negative 13 plus 3 times I minus 1. Remember, it's an I there, but when I'm done with it, I'm plugging in n, right, at 20. And so all I need to do is figure out how many terms I have. So n is what? How many terms do I have? Well, what's my last term? The 20th term. And how many terms did I skip? If I started at the 8th term, how many terms did I skip?
12.
I started at the 8th. So I skipped 7 terms, right? A sub 1, A sub 2, right? So 20 minus 7 is 13. So I'm doing 13 over 2, and I'm adding up the first term, which is 8, and the last term, which is 44. So 13 over 2 times 52 which is 13 times 26. $338. Right, so I gave you two arbitrary terms of an arithmetic sequence. I asked you then to find the common difference. I asked you to find the first term. I asked you to find how many terms we're talking about. That's n. And then I wanted the sum of them. Right? Kind of tricky, kind of confusing. How you feeling?
I have a question.
Yes, please.
So,
Sarah.
for the sum of the one that's, I don't know how to name it yet. So, how would you name it? The sum of the one that you just did?
Yeah. So right here, this one.
Yes. How would you name
Yeah,
it?
I mean, in general, you could say you're doing the sum of a arithmetic sequence, right? So the sum from I equals 8 to 20 of a sub I, right?
Okay. Yes. So, does it always start if I is
You can use that any
instead
letter.
of 1?
Any letter. Oh no. Oh, it can start anywhere I want it to.
Okay. So if it doesn't start at does it? How do I phrase this? So since it's I equals 8, then the first sequence of the number would be 8.
No, that was a coincidence that the eighth term was 8. Remember, so here, let's do it this way. We had figured out that the first term was, what was our first term? Negative 13. And let's start adding 3 to that. So what do I get? Negative 10, negative 7, negative 4, negative 1, 2, 5, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it was a coincidence that our the n was 8 and the term was 8.
Okay.
Right? Is that a little bit clearer?
Yes, please.
Yeah, nice.
Yeah, I only had one question.
Sure.
For the
Jamal.
n equals 20 minus 7 equals 13, the 13 is the total number of terms.
Exactly.
So
And
is that the total number of terms that wasn't included inside the 20? Okay.
Yeah, exactly. It's weird. It's a weird thought. It's like, what? And I only did one problem, so keep asking questions, everyone. That's important. So I certainly could have done the whole sum, right? I could have done the sum from I equals 1 to 20 of a sub I, right? And then subtracted off, I could have subtracted off the first 7 terms from I equals 1 to 7 of a sub I. And then I certainly should get the sum of the 8th term to the 20th term from I equals 8 to 20 of a sub I, right? And let's just see if we do that. Let's just see what happens if we do that. So let's get the whole sum. So the whole sum is 20 terms over 2. And I'm going to take the first term, which was negative 12, and the last term, which was, help me again, what was it, 44. 44, thank you. So that's the sum of all 20 terms. And I'm going to subtract off the sum of the first 7 terms. So 7 over 2. That first term, again, was negative 12. And what was the 7th term? 5, right, from here, yes? And remember, I should be getting what I got from my original problem here. So let's see. I got 10 times, help me, 32. Minus 7 over 2.
Negative 7.
Negative 7. I don't know why I don't like this. I'm doing something wrong. What am I doing wrong?
Wasn't the first one negative 13?
Oh, thank you. Yes, thank you. That's what I'm doing wrong. Thank you for saving me. Please, always when I make mistakes. So 10, yeah, so negative 13 plus 44 is what, 31. And then I've got a negative 7 over 2 times, that's better, even number, right? Negative 8. So I've got 310 plus 28, 338. Ha! Same answer. So look, it's new for you, right? You're confused a little bit, like, and then it doesn't help if I make a mistake, but forgive me, I am human. But you just got to practice. You got to practice. You got to get in there. You got to do problems, and it'll become very, very easy. You'll see. Let's look at another problem, right? If that's okay, can we move on to one more? Then I should probably prove this new formula. So here's our list of problems. Like the first one says, show their arithmetic. Number 7 through number 16 says, show their arithmetic. And it's pretty darn obvious that they're arithmetic because you can see mx plus b, right? All of them are in mx plus b. There's a couple of weird ones. 15 and 16 are a little bit weird, but we haven't talked about those functions yet. Number 30 looks a little bit weird. It says find the 70th term of 2 rad 5, 4 rad 5, 6 rad 5. Let's do that one. So 12.2, number 30. Find the 70th term if a sub n, curly brackets, is 2 rad 5, 4 rad 5, 6 rad 5. Obviously, we're adding 2 rad 5, right? So our common difference is 2 rad 5, right? Do you agree with that? That's easy to see. And our first term, a sub 1, is 2 rad 5, right? So our nth term is 2 rad 5 plus 2 rad 5 times n minus 1. And I want the 70th term. So a sub 70 is 2 rad 5 plus 2 rad 5 times 70 minus 1. So I like to write it like this. I have 2 rad 5s plus 69 2 rad 5s. So that's how many of them? 70 of them. So I have 140 rad 5. That's my 70th term. It's easy. You got this. And wait till you see where it comes into play in calculus. It's beautiful. And so this is one of the horrible aspects of our class, is that you don't get to see where these things, how they turn into such beautiful things until next semester, right? So you gotta trust me on this. Trust me because I've been through it. Trust me that I'm trying to get you ready for Calc 1. I'm going, I don't care about Calc 2. Which sucks because I'm going to probably see some of you in Calc 2, and so I don't want you to be horrible at Calc 2, but I know we can't remember all of this stuff for Calc 2. We're going to just try and remember as much as we can for Calc 1, right? All right, I should probably prove, and I'm going to prove this, but you don't have to write it down, okay? I'm not going to ask you proofs. You're not responsible for proofs on exams. I am going to do a couple of other proofs in the next 2 classes. By the way, our next class is Wednesday, right? We don't have class Monday. But if I put one of those proofs on the test, it would be extra credit, okay? I do think the computer scientists should know the proofs. If you're a math major, you should know the proofs. But what we do in 12.4, which I'll start today, is something that the computer science students will also do in Computer Science 207 or discrete structures, Math 207. They're both the 207, but one is taught by computer science teacher, one is taught by math teachers. They're both the same course. So again, I'm writing the proof. You don't really have to, okay? So I want to show that the sum from k equals 1 to n of a sub k is n over 2 times the sum of the first term and the last term. So I want to show that that's true, right? And I guess I kind of need a recursive formula for, well, I don't know if I do, but I want to look at a sub n as a sub n plus d times n minus 1. I want to see what happens if I start to write out a bunch of terms here, right? If I start to write out a bunch of terms, what am I going to get? So, meaning a sub 1 is a sub 1, duh. A sub 2 is a sub 1 plus d times 2 minus 1, right? So you can see a sub 1 in there, right? But look at, and so, well, when I simplify this, I get a sub 1 plus d, right? And so you're going to see that I get a sub 1 plus 2d for the next one. I don't even have to write that out, right? You can agree, right? The n minus 1 is going to become 3 minus 1, which is 2, right? So you can kind of see that what am I going to get for a sub n? Right? I'm just going to keep. It doesn't. I don't know what I'm doing. Why I'm doing this for, but a sub n is obviously is that last one. That's the last term. It's the first term and it's the last term, right? When I'm plugging in the last term, I'm picking some value of n, right? Okay, so I just need that for my proof. So it was probably not that important that I did it, but I want you to see that this guy represents the last term, right? The nth term, right? Okay, so I'm going to start with my sum from k equals 1 to n of a sub k, and that's going to be the sum from k equals 1 to n of a sub 1 plus d times n minus 1. Right? I put in that general form here. Now, again, you don't need to copy this, but I just want you to agree with every step, right? So don't let me cheat you. So I'm going to distribute the d here. So this is the sum of k equals 1 to n of a sub 1 plus nd minus d. And now I'm going to distribute my sum, right? So I need the sum of a sub 1 plus d times the sum. Oh, this should be a k. Sorry, mistake. Sum of d times the sum of k minus the sum of d. And each of those we know, right? Each of those we know from last class. What's the sum of a1? If I add a1 up n times, what do I get? I get n times a1, right? And when I add up the index k, I get n times n plus 1 all over 2, right? And when I add up d n times, I get n times d. That part, let's make sure we agree with that part, right? And I'd say everybody, but Jamal would be able to agree with me here, right? When I add up a constant, I get n times the constant. So there's my n times the constant. And when I add up the indices, k, I get n times n plus 1 all over 2, right? We did that last class. I'm going to prove that again today. I can factor out an n from upstairs and a 2 from downstairs. So I'm going to factor out an n over 2. So I need a 2 times a sub 1 plus d times n plus 1 minus 2d. Now, when I factor out that 2 from downstairs, obviously this 2 disappears. But you should agree with me, at least when I distribute that 2 back in, the other 2's cancel, right? When I distribute that 2, that's a 1/2. When I distribute the 1/2, the other 2's cancel. So you should agree with the factoring. I'm going to distribute my d again here. So I get nd plus d minus 2d. Right, so I'm distributing that d here. Everything should be agreeable. And I've got 2 times that first term. D minus 2d is minus d. So I get plus nd minus d. And I'm going to factor out the d. And I get a d times n minus 1. That shouldn't be a shock. But you're going to see I'm going to split up my... Go ahead.
You split the 2a for 1.
Yeah, I'm going to split the 2a sub 1. So I'm going to turn it into a sub 1 plus another a sub 1. And you can see here, what do I have in yellow? I have my last term. Right? So there it is. The sum is n over 2 times the sum of the first term and the last term. QED. QED is just a little thing we say. It's Latin for I told you so. Quadrant demonstrato. So there's the proof, right? That I can get the sum, finite arithmetic sequence, the sum of a finite arithmetic sequence just by knowing the first term and the last term. Nice. So we're done with 12.2. So you should be able to finish homework 12.1 and 12.2. I would like you to, I'm going to start 12.4 now. We're skipping 12.3. That will happen. That will be hopefully taught to you in Calc 2. It's section 2, 8.2 in your Calc 2 book. But I want to do section 12.4, right? And that's it for chapter 12. I won't finish it today, so I'll finish it Wednesday. So you should be reading 12.1, 12.2, 12.4, and you can start reading chapter 2. We're going to do 5 sections of chapter 2. And about a week after I finish that will be your first test. Okay? So I try to give you at least a whole weekend before you take a test. Right, at least a weekend before you'd be assessed on what you learned, right? I certainly need a weekend plus a class at least, because you should be able to ask questions, before the test. And I give test reviews, and they're very similar to the test, so it's not going to be difficult. Meaning if you can do the test review, you can do the test. Okay. So I want to talk about 12.4. How are we doing? We okay? We feeling comfortable here? Nice.
Kind
of. Nice.
Nice.
Who is that? Abraham? Kind of. Yeah, kind of, because we only did a couple problems and you got to get into it, right? You got to just start doing some work.
Yeah, for sure.
Yeah. It's understandable, right? So, I'm not worried about anybody yet. So 12.4, we're talking about proofs by induction. Proofs by induction. And it's a little bit strange. This is really important for us computer scientists. It's important for the rest of us because these things are going to be used quite a bit already in our course and in Calc 1 and Calc 2. Do we use them in Calc 3? No. So in Calc 1 and Calc 2 we use them. Okay. But the basic idea is I'm going to recognize something being true when I evaluate it at 1. So this is, of course, related to these series and sequences. First, it seems to be true for the first time it happened. It seems to be true for the second time it happened. It's true for the third time it happened. I think it's always going to be true. So what I do is assume it's true sometime later, and then see if it's true for the very next time, and then I know it's true, right? So I pick an arbitrary time later, or an arbitrary value of n, and see if it's true for the one right after it. So the example I like to give is, well, yesterday the sun rose, right? Today the sun rose. It's really nice out today, actually. Tomorrow I'm thinking the sun is going to rise, right? So let's assume it's going to rise sometime in the future, and then see if it happens the very next day after. And if it does happen, then I can assume the sun is always going to rise. Of course it's not, right? We already know the sun is going to burn out eventually. But we'll all be long gone, hopefully. So, but that's the basic process of induction. So here we go. What's my process? Step 1. Show the equation is true for n equal 1, maybe 2, maybe 3. Step 2, assume, and of course we know what happens when you assume. You make an ass out of you and me, but we have to assume things to prove things in math. Assume it is true for some n equal k, so some number later down the line. Step 3, show it is true for, this is some, S-O-M-E, right, for n equal k plus 1. And then we know it's always true. So if we show it's true at the beginning, and then assume it's true some arbitrary time later, and then it happens that we can then show it true even after that, then we know it's always going to be true, right? The key here is that I pick that arbitrary number for n. The secret to this is to know the next term, right? So the secret to understanding these proofs is know or find the next term. That'll make more sense when I do it, okay? Find the next term. If you can find the next term, you've got the secret that we need to prove these, okay? This type of question, so I don't care if you do homework 12.4. I think if you're a computer scientist, you should do 12.4. It's hard to write MathXL to do proofs, so it's a little strange. So if I put one of these on, it would be extra credit, okay? I would expect my computer science majors to do it. Everybody else can give a little break on that. So, but if you skip the extra credit, you can still get 100 on the test, right? Yeah. So, so here we go. We're going to do our first proof, right? So we want to prove that from I equals 1 to n of the indices I, that I get n times n plus 1 all over 2. And remember, I proved this to you using Gauss's method. So now I'm going to prove it using induction. So, proof. let n equal 1. Oh, and by the way, what is this? This is 1 plus 2, right? It's the sum of the indices. First index is 1, second index is 2, third index is 3, plus dot, dot, dot. The last index is I, right? Sorry, n, right? Remember what my secret was. What's the next term? Can you tell me what the next term is right away here?
4.
Oh, yes, 4, but remember I got plus dot, 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 plus n. So what happens after n?
Infinity.
Nope, right before, it's before infinity.
I wouldn't know.
Yeah, so anybody, right? Anybody. So if my very last number was 10, you can tell me the next number is 11, right? So if my last number is n, what's the next number?
And then minus 1.
Yeah, exactly. That's the secret. If you could figure out the next number, this is very easy, okay? Now, sometimes figuring out the next number is not so easy, and we'll see. We'll see that Wednesday. Okay, so I let n be 1. I want to show that the sum from I equals 1 to 1 of I, which is just 1, is also true on the right-hand side when I plug in 1, right? So that's 1 times 1 plus 1 all over 2. That's 2 over 2. That's 1. It's true, right? So it's true for when n is 1. If I sum up at the first index, I get 1. And if I use that formula on the right side, I also get 1. Wilder, you with me there? Question? Wilder?
No, sorry.
It's no problem. No problem. Just want to make sure you get your questions answered. So let's see if it's true for n is 2. Let n equal 2. So I'm looking at the sum from I equals 1 to 2, which of course is 1 plus 2, right? I'm adding up the first two terms, right? Which is 3, right? But let's see if I get the same from my right-hand side. So 2 times 2 plus 1 all over 2. And that is 2 times 3 over 2, and that is 3. Oops, that is 3. Done. It worked. It worked for 1, it worked for 2, I bet you it works for 3. Right? I bet you it works for 3. Does it work for 3? Let's see. Add up 1, 2, and 3. What do you get? 6, right?
6.
Yep, so 6, right? If I let n equal 3, what do I get when 3 times 3 plus 1 all over 2? Do I get 6 again? Yes. So it's working. It works for 1, it works for 2, it works for 3. So now I'm going to assume it works for some number later. I don't know what number, right? Sometime in the future. Assume that the sum from I equal 1 to k of I, which is 1 plus 2 plus 3 plus 4 plus dot, 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 plus k, is equal to k times k plus 1 over 2. Now, yes, all I've done is replaced n with k, but I'm saying to you, k is some different number down the road. Maybe 3 billion. Maybe it's 72. I don't know. It's arbitrary, right? It's just a number past where I've already tested. I want to show that the very next term is going to be true as well, right? So I'm assuming this is true, and my secret is to add the next term, and you all have already told me it's k plus 1. So I'm adding k plus 1. So because k plus 1 is just some number, I have not changed the equality here, right? I've got 3 things that are equal to each other. If I add the same number to those things, which is the next term, I still keep my equality. So what do I have on the left now? Notice that on the left-hand side, I don't have the sum up to k anymore, right? What do I have the sum up to? I have the sum up to
K plus
k
1.
plus 1. Okay. Now on the right-hand side, I don't touch it, right? On the right-hand side, I don't touch it. So, but I still have this whole, this whole right-hand side here, right? right? So I have that right-hand side, and that's where the magic is going to happen. I'm going to manipulate that right-hand side, okay? So I can get a common denominator here, right, of a 2. And I could factor out now, I could factor out a k plus 1 over 2. So I'm going to factor out a k plus 1 over 2. And then what's left over is going to be a k plus 2. And remember, what I was trying to prove this for k plus 1, right? So I'm saying now that n is k plus 1, right? So with n equal k plus 1, what do I get? I've got a k plus 1 over 2 times a k plus 1 plus 1, right? And now I'm going to take every k plus 1 and replace it with an n. And look at what I get. I get n over 2 times n plus 1. And that's it. That's that we already know. That's the formula. That's what we're trying to prove.
Question.
Yes.
Do we have to put QED after every proof?
Yeah, I guess I should. Well, you don't have to. It's a way of saying the proof is over.
Okay.
It's almost like, you know, the movie's over when the credits roll, right? So there's, yeah, it's just like some people put W to the 5, and that's which was what we wanted. Some stupid. It's just a bunch of math nerds making up how to end a proof. But when they proved it in ancient Greek, they would, when they proved something in ancient Greece, they would say quaderat demonstrato, which was what I wanted. Right? I really should put a conclusion. So conclude. So the sum of I equal 1 to n of I is n times n plus 1 over 2 is true by induction. And then you can put your little signature there. Ta-da! Whatever. So I don't want to do any more than that today. And that's nice because it's Friday. So why not get out a little bit early on Friday? But any general